This is SpaceTime Series 26, Episode 34. Coming up on SpaceTime, current volcanic activity finally discovered on the planet Venus. Looking back to first light and the beginning of everything. And NASA shows off its new Artemis spacesuit. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Well, there have been lots of hints, but now astronomers have finally discovered direct geological evidence of current volcanic activity on the surface of Venus. The findings, reported in the journal Science, are based on a detailed re-examination of archival radar images of Venus taken more than 30 years ago in the 1990s by NASA's Magellan spacecraft. The images have revealed a volcanic vent which has clearly changed its shape and increased significantly in size over the space of less than a year. Scientists study active volcanoes to understand how a planet's interior can shape the crust, drive its evolution, and affect habitability. The study's lead author, Robert Herrick from the University of Alaska in Fairbanks, says he wasn't really expecting to find anything, but after about 200 hours of manually comparing images from different Magellan orbits, he saw two images of the same region, which were taken 8 months apart, which were exhibiting telltale geological changes caused by a volcanic eruption. Herrick's a member of NASA's Venus Emissivity Radio Science INSA Topography and Spectroscopy, or VERITAS mission, which will fly to Venus in about a decade in order to study the planet from the surface right through to its core, in order to better understand how a rocky planet about the same size as the Earth could look so very different and have gone down such a very different evolutionary path, developing into a world covered in volcanic plains and a deformed terrain hidden beneath a thick, hot, toxic atmosphere. The geological changes that Herrick found occurred in Alta Regio, a vast highland region near Venus's equator, which hosts two of the planet's biggest volcanoes, Osamons and Matmons. The region has long been thought to be volcanically active, but up until now, there's been no direct evidence of any recent activity. While scrutinizing the Magellan radar images, Herrick identified a volcanic vent associated with Mount Mons that appeared to have changed significantly in shape between February and October in 1991. In the February image, the vent appeared nearly circular, covering an area of less than 2.2 square kilometres. It had steep interior sides and showed clear signs of drained volcanic lava in exterior slopes, factors which hinted at past activity. However, in the Magellan radar images captured just 8 months later, the same vent had nearly doubled in size and had become quite misshapen, and it also appeared to be filled to the brim with a lava lake. However, because the two observations were from opposite viewing angles, they had different perspectives, which made them difficult to compare. And the low resolution of the 3-decade-old data only made the situation worse. So Herrick teamed up with Scott Hensley, NASA's Jet Propulsion Laboratory in Pasadena, California, who's project scientist for VERITAS and a specialist in analyzing radar data like Magellan's. The pair created computer models of the vent in various different configurations in order to test different types of geological event scenarios, and from those models they were able to conclude that only an eruption could have caused the changes they saw. When it reaches Venus, VERITAS will use state-of-the-art synthetic aperture radar to create three-dimensional global maps and a near-infrared spectrometer to figure out what the surface is made of. The spacecraft will also measure the planet's gravitational field in order to determine the structure of its interior. Together, these instruments will offer clues about the planet's past and present geological processes. VERITAS, together with NASA's Deep Atmosphere Venus Investigation of Noble Gases or Da Vinci mission, was selected in 2021 under NASA's Discovery program as the agency's next missions to Venus. As well as being Earth's planetary neighbour, Venus is also considered to be Earth's sister planet. They're both almost the same size, with a similar mass and diameter, and they were formed under the same conditions, in the same part of the solar system, and out of the same materials. In fact, Venus once excited speculation that it could host the first human colonies in space. See, scientists thought the dense cloud cover which surrounds Venus meant lots of rain. After all, it's closer to the sun than the Earth, so you'd expect temperatures to be hotter, and that would mean more water evaporation and hence more rain clouds. So scientists envisioned that under all those thick clouds, Earth's sister planet was covered in lush green tropical rainforests. Think of the Amazon on steroids. But reality was very different. Soviet and American probes visiting Venus have found it to be the closest thing to hell in our solar system. Venus has a runaway greenhouse effect. Its surface is scorchingly hot, with average temperatures of 462 degrees Celsius. That's hot enough to melt lead. And as for those thick, opaque clouds which shroud the planet, well, they do cause rain, but the rain isn't water. Instead, it's droplets of metal-eating sulfuric acid. Scientists have seen what look like snow caps on some of Venus's tall mountain ranges, but the snow isn't frozen water. It's actually metallic. And those planet-hugging clouds are so heavy, they crush Venus's carbon dioxide-rich atmosphere, acting like a lid on a pressure cooker, giving the planet a surface pressure some 92 times greater than the average sea level surface pressure on Earth. So visiting Venus would see you poisoned, crushed, broiled, and toasted. And the weirdness doesn't end there. Venus rotates in retrograde compared to most other planets in the solar system, including the Earth. That means that on Venus the sun rises in the west and sets in the east. But it rotates incredibly slowly. A day on Venus lasts some 243 Earth days. Now, Venus's year is 224.7 Earth days. That's how long it takes Venus to orbit the Sun. So that means a day on Venus actually lasts longer than a Venusian year. This is space-time. Still to come, looking back at the first light and the beginning of everything. And NASA shows off its new Artemis spacesuit. All that and more still to come on Space-Time. New research using an array of antennas in the Australian outback have been able to reduce cosmic background noise, bringing astronomers closer to solving a 13.5 billion-year-old mystery. The period immediately following the Big Bang, when the universe was created 13.82 billion years ago, resulted in a universe without light. It's a period astronomers refer to as the Cosmic Dark Ages. Instead, the early universe was filled with a hot soup of opaque particles, primarily hydrogen and helium atoms with a little bit of lithium and beryllium. These are the particles created in the Big Bang. There were no other elements. Eventually, these started to condense to form neutral hydrogen clouds. And those clouds eventually began to coalesce under their own gravity to form the very first stars. As these stars began to shine, they generated ultraviolet radiation, which began to clarify the opaque universe by ionizing the hydrogen in what astronomers called the epoch of reionization. Now, these first stars are thought to have been very different from the sorts of stars we see today. Because they were made out of the pure hydrogen and helium from the Big Bang, they were theorized to have been massive, hundreds if not thousands of times bigger, brighter and hotter than the Sun. Being so big, however, they went through their nuclear fuel supplies incredibly quickly, only living for a few 100,000 years or maybe a couple of million. Their like has never been seen again. During their lives and as they died, they began to fill the universe with all the other elements we see on the periodic table, and these elements were incorporated into the successive generations of stars. They gave rise to the galaxies, stars, planets, and even people we see today. We are all star stuff, and these first stars is where it all began. Studying this ancient time when the first stars and galaxies formed is crucial to science's understanding of the universe and its evolution up until today. But that's a task easier said than done. The signals, which started life as a hydrogen atom radio wavelength of 21 centimeters, are incredibly weak, and the background noise of the universe, well, it's incredibly loud. Over the intervening billions of years that signal has been travelling through space, it's also been stretched thanks to the physical expansion of space-time itself, and consequently it's grown even fainter. It's a problem Dr. Christine Lynch from Astro 3D, the AID Centre of Excellence for all-sky astrophysics in 3 dimensions, together with fellow scientists, are continuing to work on today. Lynch is the lead author of a paper about the research, which has now been reported in the publications of the Astronomical Society of Australia. Lynch, together with colleagues from Curtin University and the International Centre for Radio Astronomy Research, have been able to reduce the background noise in their observations, thereby allowing them to home in better on this elusive signal. To achieve this, the team worked with new equipment installed on the Murchison Wide Field Array radio telescope located in outback Western Australia, some 800 kilometres north of Perth. The Murchison Wide Field Array began operations over a decade ago. One of its aims has been to find the radio wave signature from the first light, that period known as the epoch of reionization. The array comprises multiple low-frequency antenna tiles, which search the skies for the faint remnant of the outpouring of ionized hydrogen atoms that accompanied first light, which we now think began around 300 million years after the Big Bang. Recently, the number of antenna tiles were doubled from 128 to 256, thereby significantly extending the land area occupied by the facility, but also greatly upping its power. By combining some of the existing tiles with 56 of the new ones, the authors were able to run a new sky experiment called the Long Baseline Epoch of Reionization Survey, or LOBES, in order to refine the hunt for the long sought-after signal. Lynch says the challenge is that the universe is very crowded and there are too many other radio sources that are much brighter than the epoch of reionization signal, which lie between us and the signal's origins. She says it's a bit like trying to hear somebody whispering across a room when between you and that person there are thousands of other people all shouting as loudly as possible. But by using the new tiles and thus expanding the physical area over which the antenna works, Lynch and colleagues were able to reduce a lot of that interference. As more and more of the tiles are added in, they'll have an even better chance of finally finding the echo for the first light. They've so far surveyed more than 80,000 radar signal sources, taking 16 spectral measurements for each. Running the results, they've produced some real and simulated models in which the noisiest foreground radio signals were reduced by a factor of 3. Lynch says it's the deepest and most detailed view to date of the radio sky in these epoch of reionization fields, and the new research provides astronomers with a clearer path for locating the signal, a detection that will be a major achievement in astronomy.
So the epoch of reionization is kind of this time period where the universe transitions from the dark ages, where there's no sources of light. So there are no stars, no galaxies. It's just mostly neutral hydrogen, a little bit of helium, a little bit of elements that are higher mass than that, but mostly just neutral hydrogen. And that neutral hydrogen kind of coalesces based off of gravity. Real basic physics, just gravity is pulling things together. There's dark matter behind all this, so that's helping all the neutral hydrogen kind of clump together. And then the epoch of reionization really starts happening when those clumps of neutral hydrogen start turning into stars and galaxies.
And in the process, that reionizes the universe slowly over time, and it starts to look the way it does now.
Yeah, so those stars and galaxies start producing photons, and those photons ionize all of the neutral hydrogen around them, and until you get to a universe that's like ours, where it's mostly not neutral hydrogen, it's mostly ionized hydrogen, and you get all the stars and galaxies that we see today. So it's kind of this pivotal period where the universe goes through this transition of being mostly dark to having these sources of light.
And your research has been trying to, for want of a better term, see this, at least in radio.
Yeah, so the idea is that we can detect that reionization process through radio waves. And so we're trying to actually understand those first stars and galaxies using radio telescopes, because we can kind of detect their signatures in the radio. So we can just know more about them. We don't really know a lot about how big they were, what they were made of, what was actually doing the ionizing. Was it stars? Was it black holes accreting matter onto them?
That's a whole different topic, isn't it? The idea of whether or not primordial black holes even existed, which they should have based on the amount of density that would have been there. But
so there's a lot of open questions about what actually was around at the beginning and, how did that all transition to what we see now? And so we have all these models, but they're mostly just, they're based off some really fundamental physics that we understand really well, but we don't have those measurements of the initial conditions to say, this is how it all started. Now take it from there in your model and see what happens and see if we get what we see.
If we go back another, say, 250, maybe 300 million years, even earlier, then we're at the cosmic microwave background radiation, the time when the first atoms were formed. Is this the same sort of thing in that the reionization should be everywhere?
Yeah, exactly. So basically, we should be able to detect it wherever we point our telescope. It should be kind of in the same way that the CMB is everywhere in kind of this uniform, but it still has these kind of smaller structures that tell us something about the structures on a large scale at the beginning of the universe. Reionized hydrogen, or the neutral hydrogen signatures that we're looking for, will be the same, but we tend to choose places to look where the sky is kind of not as bright. So where there are less complex galaxies in the field or less emission from our own galaxy in that field. So it just makes it easier to detect the signal. So that's kind of how we choose where to look. It's not really that the signal should be brighter in that part of the sky. It's just that there's less bright stuff in the way.
And I guess that's part of the problem, isn't it? Because as we've found out with things like the Hubble Deep Field and Ultra Deep Field, really, if you look at the darkest patch of the sky where there doesn't seem to be anything, once you start looking deep enough, there's still lots of stuff there. It's everywhere.
Yeah, exactly. So, and we're looking in the radio. So the brightest objects in the radio are not stars. They're galaxies. When you look at an image that's from a radio telescope, you're looking at thousands of galaxies in that field. And so what we're trying to do is study the fields that we're using to make this measurement so that we can understand what kinds of galaxies, what kinds of emissions are in that field, so that we can then model it and remove it from our data. And then hopefully be able to detect the signal that is from the reionization period that lays kind of beneath all of that.
And this is where the Murchison Wide Field Array comes in.
Yeah, so we're doing we have our own EOR experiment, an epoch of reionization experiment using the MWA, but we also use the MWA. It's very nice that we can do this with the MWA. We use it to actually model the sky. So right now the MWA has two different configurations, and the configuration I used was to use the one with the best imaging properties. And this is just because the array has now been spread out over a larger area on the ground. And so that kind of translates into better angular resolution and better imaging. But being able to have those nice new properties of the array means that we get a better image of the sky. And then you can do modeling of those images and remove the sources better, these galaxies that are in our way. You can remove more of their emission. But it's nice because the MWA second configuration is what we use for the actual experiment. So we can make these models using our telescope, and then we can also do the experiment with the same telescope. And so that means that we can kind of limit the number of systematics that are affecting our models and our data.
Tell me about the work.
We generally observe at frequencies that are between 100 and 200 megahertz to look for these signals. And we have to use a telescope like the Murchison Wide Field Array, not just because it's a low-frequency radio telescope, but also because it's out in the middle of the desert and there are no other radio sources. So cell phones and radios also operate at the same frequency, so they will dominate any signal that we're trying to detect. But yeah, so we're using this telescope to try to detect these signals, and it's a very difficult experiment. It's very challenging, and that's why there's such a large group of us, because we're all very highly skilled in our own little problem that we're trying to solve. And then once we all solve our own problem, it comes into a larger kind of collective solution to try to detect these signals.
Once you eliminate all the other signals, the signals that aren't what you're looking for, what are you left with? What will these radio signals tell you?
Right. So the hope is that if we can eliminate all of the astronomical and terrestrial radio signals that might be in our data, that what you'd be left with is a signal that's dominated by the radio signal, the emission coming from the reionization. So far, we haven't been able to do that, not just because our astronomical models aren't good enough, but there's also a lot of bad data or errors associated with our calibration that cause kind of excess emissions in the data. So what we've been really focused on is trying to make our calibrations more precise and to eliminate kind of these systematics that we're hitting, in the hope that we can finally get down to where we expect the signal to actually lie and be the dominant thing in our data.
We're talking about galaxies here, in very primordial galaxies, very early in their existence.
Yeah, so these are galaxies that would have formed within the first 500 million years to a billion years after the Big Bang. So yeah, the first ones that we think existed in the universe.
Murchison's one of the precursor projects for the Square Kilometre Array. How will that help?
Yeah, so the Murchison Wide Field Array, as you said, is a precursor to the Square Kilometre Array. And the thing about the Square Kilometre Array is that it's going to have many more kind of tiles of antennae, and it will cover a larger area on the ground. So it will be much more sensitive than the Murchison Wide Field Array.
So better resolution.
And that means that, yeah, so the resolution will be better, but just the instrument sensitivity, the noise that's associated with that instrument is going to be much lower than for the Murchison Wide Field Array. And what that means is that the Murchison Wide Field Array right now can't actually make images of the signal we're looking for. We're actually doing a statistical detection. So we do some fancy math and across our data, and we look at the result and try to see if that is the signal that we expect. But we're not actually making images. It's basically a fancy statistical analysis that we're doing. But with the Square Kilometre Array, we will be able to make those images because it'll be sensitive enough to actually image the emission that we're looking at. So that's kind of the advantage, is SKA will just give us more information from the images that we can't really get with the Murchison Wide Field Array.
Will the images be similar to, again, the cosmic microwave background? Is that the sort of thing?
Yeah. They would,
dense areas and less dense areas?
Yeah, so it will... It's not so much that it'll be more dense or less dense. It'll be more ionized or less ionized regions of hydrogen.
That's Dr. Christine Lynch from Astro 3D, the ARC Centre of Excellence for All-Sky Astrophysics in 3 Dimensions, and the Curtin University node of the International Centre for Radio Astronomy Research. This is SpaceTime. Still to come, NASA shows off its new Artemis II spacesuits. And later in the science report, Australia to purchase between 3 and 5 Virginia-class nuclear submarines, as well as building a further 8 nuclear subs locally. All that and more still to come on SpaceTime. NASA has shown off its latest prototype spacesuits, destined for use on the Artemis II mission, which will return humans to the lunar surface. Developed by Axiom Space under NASA supervision, the new spacesuits are called the Axiom Extravehicle Mobility Unit, or AXIMU. They'll provide greater flexibility and durability than the current generation of spacesuits, which are developed for the Space Shuttle and use on the International Space Station, and were based on the earlier Apollo spacesuits worn by the astronauts who walked on the Moon back in the 1960s and 70s. The Apollo spacesuits went through several versions, but it was the A7LB which became famous for astronauts walking on the Moon and working aboard the Skylab space station. The A7LB suits were worn for all phases of the mission, from launch to EVA or extravehicular activity, as NASA speak for spacewalk, and for the return to Earth landing. They were designed to have good upper body mobility and to facilitate walking on the lunar surface, and even driving in the lunar rover. But one problem no one anticipated was how sharp lunar dust would be. Lunar dust became a real problem. As well as being sharp, it's extremely fine, and so it gets in everywhere, at least on the outside of the suit. And the sharp cutting edges of these dust pieces posed a real threat to cut through the spacesuit material. The current spacesuit, which developed from the Apollo suit for EVAs for the Space Shuttle, is assembled from different sized components, which lock together to match the size of the astronaut wearing them. These later Space Shuttle suits were again designed to have excellent upper body mobility so astronauts could move around easily in the shuttle and perform work in space while on foot restraints. It was these suits which were upgraded during the mid-1990s for use aboard the space station and which remain in service today. Now, of course, these are all different from the so-called pumpkin suits, the ones worn during the launch and re-entry phase of a mission. The bright orange pumpkin suits included the Launch Entry Suit, or LES, and its replacement, the Advanced Crew Escape Suit, or ACES, neither of which were designed to perform EVAs, although the ACES suit is a full pressure suit. NASA's new AUKUS was developed to better deal with the lunar dust issue, while also providing good flexibility and protection for astronauts during EVAs. Now, the suit on display for the media had a very stylish black covering, but that's only temporary rather than being a fashion statement. It will be replaced by white material which will reflect heat better and be easy to see against the blackness of space. NASA chose to use a commercial services contract for development of the new spacesuits, whereby NASA is purchasing moonwalking services from Axiom Space. NASA simply defined the technical and safety standards by which the spacesuits needed to be built, and Axiom Space agreed to meet these key agency requirements. But following the Artemis II mission, NASA will complete future Artemis missions under a new Exploration Extravehicular Activity Services contract. NASA will be using this contract to meet the agency's spacewalking needs for both the Moon and the International Space Station. The agency recently awarded a task order to Collins Aerospace, who is also competing within the contract to develop new spacesuits for astronauts to wear during spacewalks on the space station. So both vendors, Axiom and Collins, will compete for future spacewalking and moonwalking contracts. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. Australia is purchasing at least 3 and possibly up to 5 American Virginia-class nuclear submarines from the United States Navy. It will also build an additional 8 SSN AUKUS-class nuclear submarines under a $368 billion defence deal with the United States and Great Britain. As part of the new AUKUS trilateral security pact between Australia, the United Kingdom and the United States, Adelaide's Osborne shipyard in South Australia will be upgraded to construct the new nuclear submarines, making it one of the few facilities in the world capable of building nuclear-powered subs. Under the agreement, Australian naval submariners will be embedded into American nuclear subs, and Canberra will also contribute billions of dollars towards upgrading US naval shipyards, while the United States and Britain will begin making far greater use of Australian naval bases for their own nuclear submarines. The new SSN AUKUS class will be a joint British-Australian design, so it'll also be built by the Royal Navy to replace their existing Astute-class nuclear submarines. All these moves are designed to help counter the growing military build-up by China as part of what the Chinese President Xi Jinping and his communist government describe as preparations for war. The AUKUS pact also includes cooperation on advanced cyber, artificial intelligence and autonomy, quantum technologies, undersea capabilities, hypersonic and counter-hypersonic weapons, electronic warfare, greater innovation, and information sharing. The AUKUS pact will be designed to focus primarily on military capabilities. That'll separate it from the Five Eyes intelligence sharing agreement, which includes not just Australia, the United States and Great Britain, but also New Zealand and Canada. Yet to be announced is the location of a new East Coast base for the new subs, with Brisbane, Newcastle and Port Kembla being the leading contenders. Meanwhile, Australia will purchase American-made Tomahawk cruise missiles under a new $1.3 billion deal with the United States. The medium-range guided missiles will initially be fitted to the Navy's Hobart-class destroyers and later to the Virginia-class nuclear submarines. Tomahawks are launched using a solid rocket booster, which is then jettisoned, with propulsion switching to a turbofan jet engine for the cruise phase of the flight. Tomahawks have a range of around 1,700 kilometres, depending on the version. The 6.4-metre tall missile can be fitted with a W-80 150 kiloton thermonuclear warhead, although the Australian versions will carry 450 kilograms of conventional high explosives. The missiles are currently used by the United States and Great Britain. However, Japan has just ordered 400 of them, and Australia is planning an initial order of 220. Scientists have discovered that Arctic sea ice became thinner and more uniform between 2005 and 2007, deforming and reducing to about half its previous thickness, and it's never recovered. The findings, reported in the journal Nature, are based on studies using direct measurements of the ice thickness by way of ocean moorings from the Fram Strait Arctic Outflow Observatory taken since 1990. These revealed a reduction of ice thicker than 4 metres by more than 50%. The authors say these findings are showing the longer-lasting impacts of climate change on Arctic sea ice, suggesting the change in sea ice thickness was a result of increased ocean heat in ice formation areas. The Southern Hemisphere's largest testing laboratory has just opened in Melbourne. The 8,600 square metre 3-level Symbio facility will provide an epicentre for world-leading scientific research and development. The lab will undertake analytical testing of food, agriculture, pharmaceutical products, cosmetics, water and environmental samples. It's already servicing over 8,000 clients and conducting 35,000 tests on more than 11,000 samples each week. Along with the core work, almost 40% of the lab will be dedicated to research and development, including genetically mapping human illnesses for the development of new rapid tests to detect viruses before they evolve and become more resistant to specific drug treatments, as well as tests to provide early diagnosis of cancers such as breast and ovarian cancers and chronic myeloid leukemia. A new study has found that the general public have become far more sceptical about science in the wake of the COVID-19 pandemic. The admissions by Pfizer that their vaccine was never capable of stopping the spread of COVID-19, despite all the claims to the contrary, were bad enough. But a South Australian government health official declaring a public health emergency following false claims that people were catching COVID from pizza boxes and medical advice which saw police bashing and arresting people for sitting in a public park while at the same time allowing Black Lives Matter protesters to march through the streets in their thousands compounded the problem of trust not just in science but also authority. But the cherry on top when it came to skepticism about science was evidence that the White House's chief medical advisor, Dr. Anthony Fauci, advised the very scientists who wrote the keystone scientific report about the origins of COVID-19 in the journal Nature. That crucial article played down the idea that COVID-19 was caused by a lab leak at the Wuhan Institute of Virology and instead strongly supported the idea that it most likely originated naturally in nature from mutating bat viruses. Not only did the evidence claim that Fauci later edited that study before it was published, but it also showed that Fauci's department was funding gain-of-function research into bat viruses at the Wuhan Institute of Virology at the very time of the outbreak. It's events like these which are causing a serious loss of trust in science. Tim Mendham from Australian Skeptics says the new study blames scholars who are only too eager to use their credentials and platform to clothe personal agendas in the garb of science. He says those who claim to carry the mantle of science must work daily to deserve that honour. That means asking uncomfortable questions, scrutinising studies, acknowledging personal biases, and admitting errors or uncertainties.
We have seen an increase. There was a study that was done by Gallup, looking at the levels of skepticism of science, the people of science and scientists, and trying to suggest reasons why there might be a change. If you go deeply into this particular study that came out recently, there's a lot of muddy waters in there. You can easily say, yes, one of the things this study says is that scientists pushing themselves forward as authorities and shown to be not accurate is a problem, and it is. It's always a problem. You always see these stories on the...
We saw that with Norman Swan on the ABC recently, where he was attributing deaths to COVID, which he shouldn't have done.
Yeah, there's some interesting results.
And we've seen the same thing with globally famous medical experts like Fauci, who made statements which were proven later to be untrue. That sort of thing, when you see doctors do that sort of thing, that's got to affect the credibility of science. They say trust the science, and sure, trust the science, but it's really a case of can we trust the people talking about the science?
That's right. Can you trust the scientists? And that then reflects on science itself, or at least the science in that particular area. Some of the issue you have is obviously there's the high-flying scientists, or who want to be high-flying scientists, who love the notoriety of being quoted. Then you get the scientists who get over-enthusiastic about a particular set of results, and they start reporting it before they should. And because science works in slow processes of theories and hypotheses, and then testing and peer review and going back and refining and going through the whole process over and over again until you reach a high percentage of probability or a very low percentage of probability, and you take it out of the mix. You see hear this all the time on TV programs, medical breakthrough. This is a great thing that's going to happen. Half the time it's over-enthusiastic. Yeah, it's over-enthusiastic PR department of a university, say, right? That might be sort of, let's push this. We've got this great idea, push it. And then they always have to have the caveat, yes, but we won't know for 10 years whether it actually works. It works on mice at the moment or whatever. We don't know if it's going to work on humans. So that's the preempting or preemptive pushing of science, which often turns out to be wrong. Or there's the science stars. And not all people who are high-profile supporters of science, but there are certainly people out there who get carried away by their own notoriety. Of course, it happens the same thing with people who are against science too, people who are pushing misinformation. Again, about the effect recently, a lot of information in quote, being put out about the dire effects of COVID vaccines. And you look not that deep within the evidence that they provide, you find out it's actually similarly misrepresented. So they enjoy the notoriety of putting out bad news, but actually if you look beneath it, it doesn't have a lot of substance. So scientists have to be very careful of that, but when they are careful like that, scientists should never say anything is 100% sure. But the people who are opposing them, especially spreading misinformation, will say it's 100% accurate, this is 100% guaranteed. As soon as they say that, you should mistrust them.
And that's where the problems start, isn't it? When you claim something's 100% accurate when it's not, then you start to have trust issues, and that's where the skepticism comes in.
That's right, and that skepticism and critical thinking should be an intrinsic part of all scientific activity, but it's often not, as it should also be an intrinsic part of everyday activity, quite frankly. You can apply critical thinking anywhere.
Science is always, as you said earlier, it's building towards a conclusion, and sometimes the conclusion is not what you expect it to be. But that's what science is. It's a trial and error thing, and we evolve from what we learn because people want absolutes, and when they don't get those absolutes, they become cynical.
Absolutely, that's right. And the trouble is they don't just want absolute information, they want absolute information now, right? They say, I'm not going to wait 10 years to see if what you're saying is going to work out to be true. I need the information now. Now, some poor scientists will fall for that trap in their enthusiasm, quite genuine enthusiasm, perhaps, and that's not the thing they should do. But being restrained is the other problem, that people want information now, or they want 100% reliability. The interesting thing about this particular article that was looking at the increase in skepticism of science is the article actually doesn't say that specifically. Okay, this is a slight problem when you do become skeptical and you read between the lines. Actually, you don't have to read very far between the lines. What it was based on is 2 Gallup surveys looking at, do you believe science is real, right? Which is a pretty broad statement. Science is real. Are the results of science real? Probably the better question. And people were asked yes a lot, no, etc. But the first survey was done in 1975, and the second survey was done in 2021. So you're talking 45 years between these 2 surveys. And there's a lot of things that have happened in those 45 years, not just the pandemic, that might positively or negatively reflect on science and scientists. So there was a jump, certainly, when people looked at this thing to say, pandemic, COVID, scientists saying things they shouldn't say, or lying, or whatever, or being over-enthusiastic. And this survey is actually not as clear-cut as that. But this is over this 45-year period. So as I say, a lot has happened in that 45 years, from mid-70s, for heaven's sake, up until now. So it fluctuates. And I think that to say that there's a skepticism or cynicism of science is a broad brush statement that doesn't apply to all science, doesn't necessarily apply to all areas of medicine. I mean, people aren't going to say, I mistrust paleontologists, right? And they're not going to say, I mistrust astronomers. They will say, I mistrust some medical scientists, medical researchers.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.